Hi, it's my great pleasure to present my paper on a fundamental bound on performance of non-intrusive load monitoring algorithms with application to a smart meter privacy for IFAC World Congress 2020. In this paper, we are talking about non-intrusive load monitoring. It's known that if you have smart meter measurements, you can deduce a lot of information about the household. At the very lowest level, you can find out about when people are inside the house and when they're asleep and not asleep. But using the smart meter readings, high frequency smart meter readings, we can disaggregate these readings to be able to find out when individual appliances are being used within a household. This is possible because different appliances have somewhat unique consumption patterns, so you can use those consumption patterns to figure out when each individual one is being used. A lot of non-intrusive load monitoring algorithms rely on various methods to do their job, one of them being integer programming by shifting the profile of the loads to be able to reconstruct what we are seeing in the smart meters, or using Markov models or using machine learning. Now in this paper we want to find out, would it be possible to find the lower bound on performance of all these algorithms, how good they can be, without really getting into which algorithm we are using. Now, non-intrusive load monitoring is privacy intrusive. It's enough said that there are a lot of commercial companies that are offering non-intrusive load monitoring to energy retailers and other companies, and they can really get a lot of private information of the people just based on the smart meter measurements. So there is an angle of privacy here too that we are trying to address later on in the paper. How can we use these results to be able to generate privacy-preserving load schedules? Now, to be able to have a very simple model of non-intrusive load monitoring, we consider a house with n appliances. Each appliance has a load signature, which is a kind of a unique pattern that it uses for drawing energy or power. Now, in this paper, we can both consider power measurements if our meters are in terms of power, or energy if our meters are measuring energy consumption, like smart meters, will capture the aggregate energy consumption across the house. Now we are assuming a very strong adversary that knows this load signature for different appliances. Now if we have weaker adversaries, we can think about them, the bounds that we drive in this paper as being lower bounds on the performance of those weaker adversaries. They can't be any better than this strong adversary, certainly. Now, each appliance has a designated start time tau I, and after its start time, it goes through its cycle and finishes its job. Now, the adversary does not know this tau I. The question is, can it find out these tau I's or no? Not. The total consumption of these appliances, if we didn't have anything else in the house, would have been equal to the shifted versions of the load profile summed together. Now, the adversary has access to K measurements at different times. These times could be regular or irregular, of this total consumption of these appliances plus some WK. Now these W's capture a sequence of independently and identically distributed noises. This noise can model a lot of different things, like if we have loads and appliances that we haven't considered in this setup, because a lot of those appliances might not have a unique consumption pattern, so we will not be able to think about them in this specific way. Now, we might have measurement noise, which might not be significant if we are dealing with the smart meters. We have renewable sources. If you think about renewable sources as being, for instance, generated by solar panels, and the generation of the renewable energy would vary across time based on the cloud coverage and other factors, then we would have a IID sequence of generation that's done by the renewable sources. Or the noises could be, the noises that we generate fictitiously using batteries or thermal storage to be able to ensure privacy. That's an approach that has been pursued in the smart meter privacy literature extensively in the past. Now, the adversary wants to estimate those starting time of the appliances, the tau 1 to tau n, based on its measurements that it receives from the smart meter, for instance, Y1 to YK. If we go to the very simple case of this adversary is trying to employ an unbiased estimator to find out those values, we can try to find a bound on the performance of the adversary. To be able to establish that bound, we're going to have a couple of regularity assumptions. One is that the probability density functions of the noise, the additive noise that we had earlier, is continuously differentiable. And another factor is that the value of the probability density function is equal to 0 on the boundary of its support set. Now the second one would naturally happen with all density functions that are having an infinite support, for instance, like Gaussian additive noise, and so on. The reason that we are going for this regularity assumption is that in the proofs, we rely heavily on Kramer-Rao bound. And to be able to satisfy the conditions of Kramer-Rao bound, we need these assumptions. Now, in this case that the estimator is unbiased, the variance of the error, scaled by a matrix pi, would be lower bounded, as you can see, by a trace of that matrix pi times the inverse of F matrix that we are going to get into later, divided by IW. The IW here is the Fisher information of the additive noise, W, that we got earlier there. And those R matrix that we are seeing it in the lower bound in the inverse form is a discrete cross correlation matrix between the derivatives of the loads. Now, if our loads are energy in the form of energy consumption, the derivative of them would be powered, or if they're in terms of power, then we are dealing with the derivative of the powers. If you're going for a more reasonable category of estimators, for instance, estimators that can be arbitrary and doesn't need to be unbiased, then our lower bound will become a bit more complex. If we further simplify this lower bound, we end up with the same lower bound as before, scaled by an extra term and with an additional term. Now, those extra term and additional term are functions of how much bias do we have here when we are dealing with this estimator. But the important message here is that that trace of the pi times R inverse divided by the Fisher information of W would still show itself here again too. So if we think about this as a fundamental bound, then it would show itself no matter if we have a biased estimator or an unbiased estimator. A couple of interesting things here is that if we have larger noises, so if we have like a lot of renewable energy, a lot of battery, if we have a lot of uncertainty in our measurements because of loads that we didn't model there, we would have a higher guarantee in terms of privacy, because larger noise means smaller Fisher information, and that would mean a larger lower bound here in terms of the variance of the error of the estimation. And another important thing that hasn't been looked around a lot in the past in terms of a smart meter privacy literature is the fact that by scheduling the appliances, we can improve the privacy, because by scheduling the appliances, we can increase the lower bound that we have here to make the variance of the error larger and larger, so that the adversary would not be able to gain any significant information about what's happening inside the household. In the limiting, we are getting a lot of regular measurements about the consumption of the household, the aggregate consumption. The lower bound that we showed earlier is going to go towards the 0, so we can deal with the rate of decrease of that lower bound, and the rate of decrease of that lower bound will be very similar to the previous lower bound. Instead of having the RD, which was the discrete cross correlation matrix, we are going to have a continuous RC, continuous cross correlation matrix. Now, it's interesting here because this lower bound becomes independent of the times that we took the samples. So when we are getting a lot of measurements, the sampling times don't really matter. Smart meter privacy by loaded scheduling. How can we do that? Is through maximizing that lower bound that I showed you earlier, particularly the part of it that has the trace of the R inverse there, over the setup schedules that are feasible for us. Now, the feasible schedules could be determined by user preferences. For instance, the user might want to run his dishwashers during the time that they are not at home, so they don't create a lot of noise, or because of physical constraints that we might not be able to satisfy all the loads at the same time because of the power ratings and the house. So what we try to do is to find the schedules that kind of have the worst case effect on the adversary. Now, this problem is highly nonlinear and non-convex. That's because the way that R relates to tau is very nonlinear and non-convex, and on top of it we have the inverse of that R matrix here showing themselves. So solving this problem is certainly not easy. What we propose here is to try to solve that approximately, or trying to find local minimizers using gradient descent algorithm. Now, to be able to do the gradient descent algorithm, we need to compute the gradient here, which is not that difficult. With a little bit of algebraic manipulation, we can find the gradient here. The gradient becomes a function of second order derivatives of the load profiles in addition to the first order derivatives, which is not really surprising. Now let's show this on an illustrative example. On a very simple example here, we have three loads here that turn on and off, and they go over a fixed period. And in addition to these three loads, we have this additional noise, which is, we are here assuming to be a zero mean Gaussian noise with a standard deviation of 0.1. Now, what can we do with these loads to make sure that the adversary would not be able to use the aggregates to reverse engineer and find out the times that we schedule each one of these loads? Now let's fix the tau 3, which is the time that we start load 3, to for instance 0, and then vary over tau 1 and tau 2, which is the time that we start load 1 and load 2. As you can see, the lower bound varies quite a lot, and there are a lot of local minimas and local maximum points. But 2 points are standouts, and those points are points that is essentially impossible for the adversary to infer if the second load or the third load was scheduled first. If you can see, the amount of the consumption for the second load and the third load is the same. So if you move them around a little bit, we would end up with a continuous consumption over a long period of time, and then the adversary would not be able to infer, if the second one started first or the third one started first. So those highest points belong, correspond to those schedules. But when we are running the local, the gradient descent algorithm to find the local minimizers, we are not guaranteed to end up with these, worst cases for the adversary. We might end up with one of other local minimizers. Now let's get into a more realistic example. In this realistic example, the loads are no longer just arbitrary on and off things. There are two realistic loads that there exist in a lot of different households, a dishwasher and a washer dryer. And again, we have an additive noise that's a Gaussian noise with a standard deviation of 0.1. Now here we are assuming that we are dealing with for instance, a normal smart meter that measures the consumption of the house on regular 30-minute intervals. Now again here, if we look at the times that we can schedule different loads, we end up with the lower bound here. We can draw the lower bound, and the lower bound would vary quite significantly based on the schedule, so we can use that to our advantage and find the schedules that give us the most amount of privacy here. As you can see again here, there are quite a lot of different local maximums in addition to a global maximum, and the global maximum corresponds to the case that the dishwasher, which has the lower consumption, can be hidden under the washer dryer with the use of the additive noise that we have there. So the adversary would not be able to infer when was the time that the dishwasher actually started its cycles. So in this paper, to summarize, we show a fundamental bound on the variance of the estimation error for non-intrusive load monitoring. We don't really care what load monitoring algorithm is used. Is it machine learning? Is it Markov chain? Is it integer programming? We just have this fundamental bound that comes from Kramer-Rao bound on how good it can actually behave. Now this fundamental bound is a function of the trace of the inverse of the cross correlation matrices. How much the loads are similar to each other kind of determines how difficult it is for an adversary to infer which load started first, which makes sense. If you have a lot of similar loads, they could be interchangeably used, and the adversary wouldn't know which one started first and which one came second, and so forth. Now, we can use these to our benefit and do load scheduling for increasing the lower bound on the variance of the error of the adversary in terms of the non-intrusive load monitoring to find the most private scenarios here, to ensure as much as privacy as we can. And in terms of future work, it would be very nice to focus on experimental demonstrations, see if what we are proposing here with the gradient descent algorithm is actually working very nice or not, if we have a lot of different loads here that we need to schedule, not only two loads. And specifically, we're going to look into commercial non-intrusive load monitoring algorithms that a lot of those companies that I mentioned earlier use, and see what's the effect of the scheduling that we are proposing here on the performance of those specific algorithms. What we are doing here theoretically, does it make sense practically or not? And that would be the two of interesting future works to do. Now, if you have any questions about this paper, feel free to send me an email or engage me on Twitter, or if you want more information about this paper, feel free to look at my webpage. Thank you very much.